Welcome back to Mathematics 0110. This lesson is about information that we can obtain from the second derivative of a function. To remind you about information we can obtain from the first derivative, recall that we can tell that a function f of x is increasing in regions wherever f prime of x is positive and is decreasing in regions wherever f prime of x is negative. We can also use the first derivative to find the critical points of the function. So those are points that can be locations of a local max or a local min. We do that by taking the first derivative and setting it equal to 0 and solving for x, and also looking at x values where the first derivative is undefined. For critical points, we need to make sure that those are in the domain of the function. You have to be able to plug the x value back into f of x in order to get a y value. If you can't do that, then it can't be the location of a local max or a local min. And the other thing we did with the first derivative was we used it to help us locate the positions of absolute max and absolute min, also called global max and global min. What we're going to do inside this section is extend the extraction of information one layer deeper. So the first derivative told us all that stuff. What does the second derivative tell us? Can we extract additional information from f of x through f double prime of x? And the answer is yes. And the extra information that we extract is about the shape of the function. I'll show you what I mean. There's three graphs here. They're all graphs containing the same 2 points, a point at 0, 0, and a point at, it looks like 4, 5. And what I'm going to show you is that if we want to connect these two dots with a curve with two stipulations. One stipulation is the curve should be continuous, and I forgot to write that, but we want a continuous curve, and we don't want to have any local max or any local min. So I'll explain what I mean with the continuous thing. I don't want to connect the dot using something like this, using a hole cut into the graph or a jump in the function or anything like that. I don't want to use a function of that type to connect the dots. And I also don't want to introduce or use a function that introduces, let's say, local max or local min in between the endpoints. So that would violate what we're being asked to do. We want to draw a curve that connects the dots without introducing max and min. So I'll show you the easiest one, a straight line. You know that one. You can connect. Okay, you can, but I apparently can't. Draw a straight line connecting those 2 points. That's one type of curve connecting the points. It doesn't have any local max, local min. It doesn't have any discontinuities. I'll show you another one. Imagine that was a string, and I'll push the string up a little bit in the middle to keep the endpoints connected or anchored down. And that's what it would look like. There's no max in the middle there. There's no top of a hill. But instead of pushing the string up, we could also push the string down in the middle, and we'd get this shape. And those are the three basic types of shapes that can connect 2 points if we're not going to allow max and min in between those 2 points. If we're just going to have a smooth curve that's always it's called monotonic. So either always increasing or always decreasing. In this case, always increasing. There are different curves within these that you could draw. I'll give you an example and I'll erase it because I don't want to clutter the graph too much. You could say, okay, I'm going to connect them with this one, except not have it curve backwards. There. I would call that part of the same family or part of the same class or part of the same category. It's a curve that has the same shape as the red one next to it, not the same shape as the one on the top right. They're fundamentally different shapes. They're bent in different directions. Well, those shapes have names. A shape or a region of a graph that looks like the top curve here is called a region that's concave up. The concavity property is, we'll see later, connected to the second derivative. If the shape looks like what's in the bottom, or a region of the shape looks like what's in the bottom, then we would say that that region is concave down. So that's just a definition. That's some vocabulary that we'll use to communicate to each other what type of curve is it, what type of shape does it have. Now notice that the first curve I drew, or actually it was the second one, is one on the bottom right. That's a concave up type of a graph. And the one at the top right is a concave down type of graph. So they're both increasing functions. If they're bank accounts, they're both saying that we're going from $0 to, and this graph's different Y value, going from $0 to $60 after some amount of time. But one of the graphs is clearly better than the other one, if this was a bank account at least. And that would be the first one, the top one. Because if you're going to project what would happen next, you would assume that it would continue with the same type of shape and would reach a much higher value much more quickly than the graph at the bottom. Another thing you can look at if you examine these graphs is the slopes of the tangent lines at different points on the graph. All the tangent lines in the top graph are below the function. They're all below the curve. You can zoom in, look at what that line appears to be, and then sketch that line out, or just take the derivative, evaluate it at some x-coordinate, that gives you the slope of the tangent line, and then get the other two ingredients to combine them and create the equation of the tangent line. If you do that for any point along that top curve, you will find that that tangent line has a positive slope because the function is increasing, and that slope is getting larger as you go left to right. It's getting slopier. So the rise over run is getting larger. The y value is more sensitive to changes, and the x value as you move from the left side to the right side. Whereas look at the bottom graph. That concave down shape has the opposite behavior. All the tangent lines are positive, so that part's the same because this is an increasing function. But look at the magnitude of the slopes as you go from the left side to the right side. So a perfectly horizontal line has a slope of 0. A very, very almost vertical line has an extremely high slope. So we're starting with a very high slope, close to 0, and the slope is getting lower or smaller or less slopey as we move to the right. That's another definition of concavity. A function that's concave up will have tangent lines below the curve, and, or equivalently, those tangent lines will be increasing as we move to the right. Whereas a curve that's concave down, the tangent lines will be above the curve inside that region, and the slope of the tangent lines is decreasing as we go from the left side to the right side. Now, in a context where we have a function f of x, we can extract the concavity extremely easily. We take the derivative of the function to find f prime, we take the second derivative to find f double prime, and then we can evaluate the second derivative at any x value that we want. If what comes out of that evaluation is a positive number, that means the function is going to be concave up. If what comes out is negative, it means the function will be concave down. So that's how we're going to operationalize the picture definition of concavity. We're going to translate it back to the derivative notation. Now why does that derivative notation match? The slope of a tangent line is the rate of change. If I'm looking at changes in those slopes, so how does the slope of the tangent line change for different tangent lines as I go from left side to the right side? I'm looking at the rate of change of the rate of change, which is the second derivative. So if the second derivative, if the rate of change of the rate of change is positive, that means the tangent line slope is increasing, and that's what's happening in the top picture. And if the rate of change of the rate of change is negative, that means the slope of the tangent line is getting smaller. It's decreasing, which is the bottom picture. Well, what do we have to be able to do? What can we extract from all of that kind of combination of theory and picture, theory and visualization? First, just a definition of concavity in terms of the second derivative, just to write it down here. We will say, by definition, that if f double prime of x is positive, it means that wherever it's positive, the function will be concave up. So if f double prime of x is positive between a and b, it means the function is positive, or is concave up between a and b. Sorry about that. If f double prime of x is negative, if it's less than 0, then that means, so let's say that that's true for values of x between a and b, then that means the function is concave down between a and b. What happens in between positives and negatives for numbers? So if positive is concave up, negative is concave down, the function switches at some point, and it switches when the output of the second derivative is a number that's between negatives and positives, which is 0. That tells us essentially all we need to know to construct a recipe for looking for where a function is concave up and concave down. We're going to need to find the second derivative, and we're going to need to set it equal to 0. Setting equal to 0 is going to tell us possible locations where a function could change its concavity. But we also have to check locations where the second derivative does not exist. This mirrors the process we had for increasing, decreasing, and max and min. Sometimes we get regions where the increasing, decreasing properties change at x values that cause the second derivative to not exist. It's going to be the exact same thing for a concavity. We can go from concave up to concave down across a location where the second derivative is undefined. So we have to look for those two. Once we have those numbers, we can make a number line, cut the number line up, and we choose test values. Now this sounds familiar. This is just what we already did to find max and min. We're doing all the same analysis, but instead of with f prime, we're doing it with f double prime. And instead of talking about increasing and decreasing, we're talking about concave up and concave down. And instead of talking about max and min, we're just talking about something that's called inflection points. And we'll define that more carefully soon. Anyways, so we cut the number line up, choose the test values, plug the test values into f double prime. If f double prime at the test value is positive, it means that whole region is concave up. If f double prime is negative, it means that whole region is concave down. It's kind of like that test value is like the representative for that region. We've drawn boundaries, and that boundary has elected a leader, and that leader is speaking on its behalf. And the whole region is going to do whatever that test value says its sign is, whether it's the second derivative is positive or negative at that test value. So let's do a concrete example. Determine where this cubic function is concave up and where this cubic function is concave down. Yes, we can draw it. Yes, we can use graphing software to draw it, but no, that's not a good way to do it. It's better to rely on an algebraic approach because it's going to give you the exact answer and not like an eyeball estimate. Okay, f prime of x, we're going to take the first derivative, 3x squared minus 6x minus 24. We do not set this to 0 because we're not interested in max and min or increasing and decreasing. The question is asking for concave up and concave down, so we have to read that and interpret what we need to do. So this means second derivative. Concave up, concave down means we're doing a second derivative analysis. Oh, that's not a good equal sign. Equals 6x minus 6. Now what do we do? Still a bad equal sign. Okay, now we set the second derivative equal to 0. We're looking for places where it can switch its behavior. So 0 equals. Now let's common factor a 6 out. Common factoring is the best way to set something equal to 0. We get one solution. Now, we don't call that a critical number. If we're doing the first derivative is set to 0, the solutions would be critical numbers, but not for the second derivative. It doesn't really have a name. It's just a special number. Okay, next, we're going to make our number line. We're going to cut our number line only at that single x coordinate that we found. If we found more x coordinates, we would cut it at several spots, but we didn't, so we can't. Okay, so there's my x is equal to 1. Next, wow, having some trouble drawing today. Next, we're going to have to choose some test values. It's arbitrary. You pick any representative of the numbers between negative infinity and 1, and that number will accurately represent its entire town, village, whatever. I'm going to pick minus 5 because it's random. And on the other side, I didn't name 1 to infinity. I'm going to pick 3. Okay, next, what do? Well, we plug them into that second derivative. I'm going to plug them into the factored form. So f double prime of x is equal to 6 times x minus 1. We're going to evaluate the second derivative at minus 5. We'll get 6 times negative 5 minus 1. So 6 times negative 6, which is negative. Now I'm not going to draw an arrow going down this time, because that means decreasing. I'm going to draw a bowl facing down, because a bowl facing down is the shape of a concave down graph. So concave down on the interval from minus infinity to 1. Now we'll do the same analysis at the other test point. F double prime at 3. We're going to get 6 times 3 minus 1. So 6 times 2. I'm not even going to calculate that. All I care about whether it's positive or negative. So it's positive. I'm going to draw an up bowl. It's concave up on the interval from 1 to infinity. All right, tougher example. Find where this function is concave up and concave down, x to the power of 2/3. So we're going to take the first derivative. The 2/3 will come down. We'll have x to the power of 2/3 subtract 1, which is minus 1/3. Now we take the second derivative. So the negative 1/3 will come down. 2 over 3 times minus 1 over 3 times x to the power of negative 1/3 minus 1. I'll do that one off to the side. Minus 1 over 3 minus 1. It's minus 1 over 3 minus 3 over 3. Oh, not equals. Minus 3 over 3, which is negative 4 over 3. Then we can simplify. The fractions multiplied together, top times top, bottom times bottom, so we get negative 2 over 9 times x to the negative 4 over 3. And we could do one more step. Since we're going to be examining this, perhaps plugging numbers into it, perhaps not. Let's rewrite this properly, x to the power of 4/3 in the denominator. Okay. Now what do? Well, we're going to look for critical numbers. There I go again. We're looking for f double prime of x is equal to 0. So negative 2 divided by 9x to the power of 4/3 is equal to 0. Let's cross multiply. That means minus 2 is equal to 0 times 9x to the power of 4/3. That means negative 2 is equal to 0, which is impossible. It will never happen. Okay, now we're going to set f double prime of x dne. Does not exist. And that means bottom is equal to 0. So if we divide by 0, then we'll get a dne. It does not exist. So that means 9x to the power of 4/3 is equal to 0. And that means x is equal to 0. We got one special x value where something interesting could happen. Okay, now we make our number line. Minus infinity to infinity. We're going to cut the number line at 0. I'm going to choose some test values. Be smart when you're picking your test values. Yes, that's arbitrary. Yeah, you can pick 7 if you want. But if you're plugging into a root like this, like a cube root to the power of 4, I mean, you can tell what the sign is, I think, without doing anything drastic. But you might as well plug in something you can take the cube root of neatly, like 1 or 8 or negative 1 or negative 8. or 27 or negative 27, like something that cube roots properly. So I'm going to pick negative 1 on this side as my test value. And I'm going to pick 8 on the other side as my test value. So these are my test values. Arbitrary, but there are better choices and bad. There's good choices and bad choices, even though it's arbitrary. Okay, next we are going to plug these test values into the second derivative. So f double prime of x is up above f double prime of minus 1. We have negative 2 divided by 9 times negative 1 to the power of 4/3. The cube root of negative 1 is negative 1, and then negative 1 to the power of 4 is positive 1. Negative 2 over 9 times 1, which is negative. That means it's concave down in that first region. On the interval from minus infinity to 0. Now we're going to choose the second test value, f double prime of 8. We get negative 2 divided by 9 times 8 to the power of 4/3. 8 to the power of 4/3, cube root of 8 is 2, 2 to the power of 4 is 16. So we get something negative again. So it's also concave down there. On the interval from 0 to infinity. So it's concave down everywhere. Now what does this look like? Because the cubic in the previous example is easy to picture compared to this. Okay, so I'm just going to make a quick graph for you. We have x to the power of 2/3. There we go. It's concave down on both sides. Something interesting is happening at 0, but it's not a change in concavity. It's concave down on the left of 0 and concave down on the right of 0. Okay. And we'll take a break and continue in the next video.